Welcome to the fourth video of this series. In this video we are going to learn some terminology about the probability, and they will help us to understand generative models in the later chapters. So the only thing that I'm expecting you to understand right now is the idea of these terms, so that we will understand better in the later chapters. And if you are not good at with math, or if you are not an engineering student, it's okay, because these terms are here just to have an idea. So let's start what we will learn today. And the terms that we are going to learn are sample space, probability density function, parametric modeling, likelihood, and maximum likelihood estimation. So let's start with sample space. Sample space is a complete set of all values that an observation X can take, okay? So it's thinking about the possibilities, basically, and I will give you some examples about these scenarios and how we can decide the sample space. For example, let's imagine you are flipping a coin, and at the end of the day, when the coin is on the ground, so we have two possibilities, right? One of them is head, or the other one is tail. So our sample space here is head or tail. So this example can be a little confusing, because I want you to forget about the minutes or seconds in the clock right now. Just focus on the numbers, okay? The hours. So what can be the sample space here? Remember, and we need to think about the overcome. So sample space here is sample space from 1 and 12. No, it's not from 1 on 12, and because at the end of the day, when we look at the clock, and if you forget about the minutes or seconds, like I say, we see 1 hour, right? For example, it's 1 o'clock, it's 2 o'clock, blah blah. So our sample space will consist of one element. And imagine you are flipping two coins at the same time, and our sample space will be what can it be? It's head tail head tail, or tail head, right? So if you are flipping them at the same time, so we have four possibilities in our sample space. So I also want to give more examples. For example, rolling a six-sided die. So when rolling a six-sided die, standard one, the sample space consists of 6 possible outcomes, which are numbers from 1 to 6. And also deck of playing cards, okay? If you are drawing one card from a standard deck of 52 playing cards, the sample space consists of all individual cards in the deck, okay? And also 2 dice rolls, okay? When rolling 2 6-sided dice, the sample space includes all possible pairs of outcomes. For example, 2-5 is one of the outcome, right? It represents rolling a 2 on the first die and the 5 on the second die. So, and let's also consider another examples. For example, weather forecast. For a weather forecast, the sample space of a various possible weather conditions that could be predicted, such as sunny, cloudy, rainy, or snowy. So in our sample space we have 4 situations, possibilities: sunny, cloudy, rainy, or snowy, right? So I just want to ask you, it's maybe a simple question: what was the sample space of our game in the previous video? I just want you to think about it, and I want you to write some more examples about the sample space in the comments below of this video. Okay, let's move on to the next slide. And the second thing that we will learn is probability density function, and otherwise we can say it PDF, okay? So I just put 2 functions here, as you can see, and I will explain them. Probability density function maps a point in sample space to a number between 0 and 1, okay? So we can say it px right now, but it's generally used like fx. It doesn't matter right now. It's a concept commonly used in probability distribution of a continuous random variable, unlike discrete random variables, okay? Which can take on a finite or countable number of values. Continuous random variables can take on any value within a specified range. The PDF provides a way to describe the likelihood of continuous random variable taking on a particle value or falling within a particle interval. So, and for example, if you want to calculate the all observations, can you see my mouse? I don't know, but I'm sure that it's visible. The all observation under this graph, the first graph, the sum of them equals to 1. So sum of them is also refers to the integral of it, right? If you take the integral, which means the area of this graph under this curve, and so you will get the result of 1. So also, if you want to find the probability of an interval, this interval here, as you can see, A and B, and the probability from A and B, we can demonstrate it, show it like this in the graph. And PDF is always non-negative, okay? And also it will help us to understand the probability better, because we will use it in our other terminology too. And let's move on to the next thing that we will learn. The third one is parametric modeling. So parametric modeling is a mathematical approach used in various fields, including statistics, engineering, computer science, blah blah. And in this approach, the model structure is defined by a fixed number of parameters, and these parameters are estimated from data to make predictions or describe relationships. It's a mathematical function, like I say, or equation, okay, that depends on a set of parameters. So these parameters capture information about the system being modeled and can be adjusted to fit observed data. The parametric models are often represented as equations or formulas. So parameters are the coefficients or constants in the mathematical model that determine its shape, behavior, or characteristics. They are typically denoted by symbols like theta 1, theta 2, theta 3, blah 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 blah. The goal of parametric modeling is often to estimate the best values for these parameters based on available data. Okay, so when you choose a appropriate parametric model, this is an essential step, okay, in the parametric modeling. The choice of the model depends on the nature of the data and the problem at hand. Different models can have different levels of complexities. So and the choice should be guided by the underlying theory and data characteristics. So let me show you. In our example in the previous video, we had P model, and let's imagine you can draw any square, any shape here. Okay, this is 5, 6, 7. You can draw any. You can draw it on any place. So, but imagine if we replace this shape, this rectangle, so it would not make sense, right? Because our data is here actually. So also let's think these two. Let's imagine we are drawing a rectangle at the left half of the plane. So but our generative model cannot produce the data like the right side of the plane, right? If you have the square on the left part, we cannot generate the data at the right part of the plane. So for example, in the rectangles, I mentioned about theta 1, theta 2, we can denote the symbols like this. For example, we can say theta 1 and theta 2 is the left bottom of this rectangle of any rectangle, and the top right is theta 3 and theta 4, okay? And we can say that theta depends on theta 1, theta 2, theta 3, and theta 4, okay? So this is also helping us, like I say, in the models, predictions, generations. And also let's check about the likelihood, okay? Likelihood in statistics, and you can see a lot of equations here. It's okay. I will explain all of them. And in statistics, likelihood is is a fundamental concept that plays a central role in statistic inference, particularly in the context of maximum likelihood estimation, which is the next term that we will learn. And the likelihood is a measure of how well a statistic model, often characterized by a set of parameters, explains observed data, and it quantifies the probability of observing the given data under the assumption that the model is true. So, likelihood, like often denoted like this, okay, like I say, measures the possibility of theta given some point x. X just was an example, was an observation in our previous video, the points, and it can denote it as like this, okay, and it describes how probable the observed data is for different values of the model parameters. So it's essentially the probability density function, PDF, or probability mass. There is another thing, it's okay to not to know right now, PMF, of the data when the parameters are fixed. So the purpose of this likelihood is to help estimate the parameters of a statistical model. In other words, it answers the question, how likely is that the model with specific parameter values would produce the data that we observed, okay? I'm repeating again, how likely is that the model with specific parameter values would produce the data we observed? So, as you can see the formula of the likelihood estimation here, as you can see in my mouth, but since this is a complex to calculate in the real time, real life, so we choose this equation, okay, as you can see here. This is a log version of this, so it's just to simplify the calculations, okay. It's often used this instead of the other one, so we just take the logarithm of it. This is the formula of it, okay. And the maximum likelihood estimation is a common method used to estimate the parameters of a statistic model, and it how can I say, it involves finding the parameter values that maximize the likelihood function. MLE, we say it. MLE seeks the parameters values that make the observed data most probable under the model. So it's, like I say, it involves finding the parameter values that maximize the likelihood function. So theta hat, as you can see, this is our MLE, okay. So in this video we learned, as you can remember, we learned some terminology about this probability, and I think it would be nice if you took your notes. It would be nice if you have a book with you or take short notes, because these probabilistic terms are used in generative models. And generative models, in the first or second video, like we said, it's probabilistic, not deterministic. So if you didn't understand the terminologies, but what I wanted to expect from you is to understand just the idea of these terms, not the mathematical expressions deeply, blah blah, you can ask under the comment section, and you can search them by yourself, okay, if you want to learn more about them. And I don't want to talk anymore in this video, and then that's why I will cut it here. So see you in the next video. In the next video we will try to figure out a really exciting and perfect thing. So see you soon. Bye bye.